Welcome. In this lecture, we will discuss the injection metallurgy, that is the submerged injection of the calcium powder. And here I will basically discuss the importance of the powder injection, that is the injection metallurgy, why it is important, and what are the different techniques for injection, and then powder injection. In this lecture specifically, we will concentrate on the powder injection through submerged lens and the kinetics of submerged injection. So, now first of all, to start with, that is the importance of the submerged injection, why it is important. First point is that there is a recovery of the volatile and the reactive addition like calcium is a major issue. Basically, we have seen now we are concerned with only the calcium powder injection, because calcium can do lot of interesting phenomena when they are injected into the steel melt. Basically, they can form some they can convert the deoxidation product into a liquid deoxidation product through the formation of calcium aluminate, as we have discussed. Also, they can modify the inclusion, they can change the shape of the inclusion in such a way such that they are not very deleterious in the service life of the product or during the further processing of the downstream processing of the steel. So, basically that is why the calcium is to be injected. But why the calcium is to be injected? Because the problem is that calcium is very reactive and volatile. As a result, if we dump it, if we dump at the top, just at the top, just like we sometimes do the alloying addition from the top and all this thing, then if we dump the calcium at the top, the major problem is that it will instantaneously react with the atmosphere and the slag. It is very reactive. So, immediately it will react with the there is the atmospheric oxygen, or it will react with the slag, forming calcium oxide, calcium sulfide, whatever it may be. So, it will not be able to come in contact with the or it can burn instantaneously. That is the thing. It is very reactive material. So, heat of reaction will be so high, so it can burn at the top. So, that is why the dumping at the top, this idea is eliminated, and then the recovery of this addition becomes very important issue, right. So, then we have to do some submerged injection. If we do the submerged injection, that is the below the melt, then the calcium will be able to react or interact with the liquid metal directly, okay, before coming to the atmosphere, okay, or in contact with the slag. They can directly react with the liquid metal. So, interaction with the liquid metal can be promoted just if we do the submerged injection. Now, as I was telling, there is a vapor pressure of calcium. If you see at 1600 degrees centigrade is around 1.8 atmosphere, is much above that 1 atmospheric pressure. So, pure calcium will try to form a bubble at liquid steel, and it will form the bubbles and go away from the system. It will just float to the top and then go away from the system. So, it is very difficult to retain the calcium even if you do the submerged injection. So, if you want to assimilate the calcium, then pure calcium injection is little difficult, because it will instantaneously form the bubbles and go away from the system, right. So, that is why calcium is usually injected in the form of an alloy. It is made either as the calcium silicide, okay, then it is injected into the metal bath. Then what happens if you make an alloy, then obviously the activity of calcium into the alloy will be less, okay. Since the activity as you know, we can define the activity this way, we know this thing, that is the activity of calcium will be is equal to your partial pressure of calcium, and that is the partial pressure of calcium in the alloy divided by partial pressure of calcium when it is pure, right. So, partial pressure of calcium, you can write activity of calcium into partial pressure of calcium when it is pure. So, this activity, it can be reduced if you just alloy it. If you make the alloy, then this activity can be reduced. And if the activity in the calcium silicide, if the activity is 0.1, then the partial pressure of calcium will be around 0.18 atmosphere. So, very less, much less than that of atmospheric 1 atmospheric pressure. So, that is the thing, the calcium usually alloyed with the silicon and which reduces its activity below 1 atmospheric pressure. So, it will not instantaneously form the bubble and go away. Of course, as soon as the silicon will also dissolve away into the melt, then the activity of calcium in the alloy may again increase and then it may form the bubble and go away. So, that is the thing, but usually the calcium silicide if you inject, then you can stop the bubbling of calcium directly instantaneously. Okay. So, that is the thing. So, you can have more time for interaction of the calcium with the liquid metal, and this interaction will be further increased if we can inject the powder just at the bottom of the ladle. That is very important. Then your time will be more. So, to derive the maximum benefit, powder should be injected at the bottom of the vessel. If you can inject at the bottom of the vessel, obviously it will take the maximum time during its rise. This is when the powder will rise through the liquid, it will take the maximum time before it joins the top slag or it go to the system, out of the system by bubbling. So, that's why there is the importance of injection metallurgy. You understand, there is the calcium cannot easily be dumped at the top, but it has to be injected submerged. Now, these are the two techniques are there. One thing is that you can inject the calcium powder using a submerged lens. This is the lens, and the powder you can inject with the help of some carrier gas, usually nitrogen, inert gas. With the nitrogen or argon, basically you can inject the powder through a submerged lens. And when you do that, then during the rise of the powder through the melt, it will react with the liquid metal and then join the top slag and the top slag. So, this is the way you can do. This is called the injection by submerged lens using some carrier gas. Another injection you can find, it is called the cold wear addition. What you do here, basically cold wear is nothing but a hollow steel casing in which the calcium powder is packed, and it looks like a ware. That is why it is called a cold ware. That is the core. In the core you have the calcium powder and the casing is simple mild steel. So, this rod, this ware, it looks like a ware and you can feed it by mechanical device into this melt, and when the ware will melt, after going inside the liquid, it will melt and release the powder. Okay. So, that is called the cold wear injection. This is by cold wear injection and this is the submerged powder injection using carrier gas. So, these two techniques are available, and we will first discuss on the this thing where the powder is injected using some submerged lens. So, now let us consider the kinetics of powder injection using the submerged lens. What is there? That thing is that this is the diagram, and you can see with the help of a flux plus carrier gas, we are injecting through a submerged lens just at the bottom, and then you can find the powder will be moving up. Now, the powder basically, powder can move as free rising liquid droplets, because the powder that will come in contact with the liquid steel, immediately it will become liquid and they will form a liquid droplet and move away. And some of the powder may be attached with the bubble, because all the powder, some of the bubble may be inside the bubble. Okay, they are just, that is called the particle inside the bubble, or bubble particles attached with the bubble. Okay, there is the, so some particle may attach with the bubbles and move with the bubble, and during their ascent they will react with the liquid metal, or there may be some free rising powder particle, liquid powder particle, when they will move, that is the black dot you can find, this is the free rising particle, and some of the bubbles and particle may be attached with the bubbles, they may also react. So, there are the two contacts. These two contacts are called the transitory contact, because during their transition the impurity transfer will take place from the metal to the slag, that is the powder particle. Okay. And there is another contact that is called the temporary, there is the permanent contact. These are the permanent contact at the top slag metal interface. This is called the permanent contact, where also the impurity transfer from the metal to the slag can take place. Okay. So, basically we have two contact, one is the permanent contact at the top slag metal interface, another is the transitory contact, And transitory contact also there can be divided into two parts. One is called the contact at the free rising powder particle, another is the contact where the particles are attached with the bubbles. Okay. So, that is the another contact. So, basically 3 reaction, and all this reaction will take place parallelly simultaneously. Okay. All 3 reaction take place parallelly at permanent contact and transitory contacts at free rising particle, that is called the FRP, and the particle attached to the free rising bubble, that is also you can call FRB. So, these are 3 contacts where the reaction will take place. So, overall rate will be the summation of 3 rates, because these 3 reactions are taking place parallelly. So, if I just show with the help of an elliptical analogy, it will look like this. This is your that is one resistance, and then this is another, this, and then. So, these 2 resistors are there, and you have suppose the metal concentration from here, there is one rate, say I1, this is your I2, and this is your I3. So, these are the 3 currents, and they are the potential difference. Potential difference you can write CMB, and here equilibrium is basically CSB by L. So, this is the equilibrium concentration of impurity in the metal phase in equilibrium with the concentration into the slag bulk, right. So, you can write it as CMB, you can simply write equilibrium. Basically, it is basically the concentration. Equilibrium is that is the equilibrium concentration into the metal bulk. If impurity concentration, that is the CS bulk. So, the reaction will take place CMB to CMB equilibrium, obviously that is the N. So, this is the gradient, and there are 3 currents are there, basically 3 rates at 3 contacts will be there. So, these 3 rates, if you can write it, then so overall rate equation you can write, this is basically the change in concentration, that is what is there, this is the total change in concentration in the metal bulk, that means how much impurity that has been transferred from the metal bulk to the what is that, slag phase or the powder particle. Okay. So, this is the amount of the impurity per unit time that is transferring from the metal to the slag, and that is the summation of this thing, that is this is the rate 1 plus rate 2 plus rate 3. Okay. So, this is the rate by permanent contact, and this is the rate through the free rising particle, and this is the rate through the FRB, that is through the bubbles. Okay. And where CMB, CSB are basically the bulk concentration of the metal and slag phases, bulk concentration of impurity basically of the metal and slag phases respectively, and TRP and TRB are the residence time, because when the free rising particle and the bubbles are moving, what is the total residence time in the liquid bath, that is given by FRP and FRB, and that is given by TRP and TRB, and L is the equilibrium partition coefficient, and then CSLF and CSGF are the concentration in the FRP and FRP when they reach the top slag. So, this is the concentration of the impurity in the powder particle when they reach the top surface, right. This is for the free rising particle, this is for the free rising bubble, there is a particle attached to the free rising bubble. So, this is the thing that will come one next. Okay. So, this is the overall rate. This is basically left hand side give you the rate at which that is the per unit time how much of impurity is transferring to the metal phase, and this is I1 plus I2 plus I3. I will come to that in details. Okay. Now, let us see the rate equation, or rather you can say the mass balance equation for sulfur transfer in the FRP. How do you do that? So, FRP, if you consider this, let us derive that equation. Simply let us consider that is this is your free rising particle, this is the free rising particle, and you have the metal bulk here, this is the metal, metal bulk, right? And suppose you have, this is your, I am just writing a fixed, that is the concentration boundary layer, sorry. This is the concentration boundary layer, right? So here what happens, you will have a concentration gradient obviously is there, that is the for metal, this is the concentration profile, it is your CMB bulk, right? And the surface, this concentration is the surface concentration, okay? And then this is the free rising particle. So whatever is the change, if you do a mass balance, that is the amount. Suppose let us consider in free rising particle, initially you have CS, you can consider it as CS liquid, okay? Liquid initially at T is equal to T, you have this concentration, right, into volume of the liquid, volume of the particle, liquid particle is this. So initially this was the concentration in the FRP at time T is equal to T, and suppose at time T is equal to delta T, you have this concentration into, if I just write VPL, this is the total mass, this minus this. So initially you have this much of, this is the concentration into volume, which is the mass of impurity that is there at time T plus delta T, and at time T this was the mass of impurity that was there in the FRP initially. So change of mass per unit time. So this is the change in concentration, not concentration, change in mass of the impurity, or you can say that is the per unit time gain in impurity, okay, gain in impurity into the FRP particle. So this is in differential form, you can simply write this thing as VPL, you can write dCS by dt. So simply you can write like this, dCS by dt. CS, okay, CS you can simply write, CS means the concentration in the slack phase, that is sufficient, okay. So this is basically, and it is positive, basically the FRP, that is the particle, is gaining the impurity. So per unit time this much impurity it is gaining, and this should be equal to, if I do the mass balance, that is the rate of, that is the, if we say the rate of transfer, that is the of impurity through the concentration boundary layer, and that can be defined as mass transfer coefficient, okay. You can call it, this flux can be defined as Km, that is the mass transfer coefficient, oh okay, mass transfer coefficient in the particle you can define it as, simply you can call it as Kp, mass transfer coefficient into the concentration difference, that is the CMB minus, I will write it as CS by L. CS is the concentration at any time T, and CS by L is basically the equilibrium concentration, that is the corresponding equilibrium composition in the metal phase. CS by L is the equilibrium concentration in the metal phase at with, that is the bulk concentration into the slack. So this is the equilibrium concentration, this is the bulk actual concentration. So this much of going there, and this is basically a flux, and you multiply it by the area, that will give you the mass. This is basically the mass per unit time, or the impurity per unit time that is crossing the concentration boundary, and that much impurity will be gained by the FRP. So if I do this mass balance simply, then we will get the, we will get this equation, that is the VPL, okay. We will get this equation, simply now we can write like this. So this is basically gain of impurity by the FRP per unit time, CS bulk I am writing, is equal to, this is the mass per unit time it is crossing the concentration boundary layer. So if I just make a flux continuity, that is the mass continuity, that is the amount of impurity that is crossing the concentration boundary layer at the FRP liquid interface, that should be equal to the amount of impurity gained by the FRP. So this is the simple rate equation, or you can say the mass balance equation at the at the FRP liquid interface. So, and then if you can integrate it during its journey, basically CSB initially, that is the concentration of the impurity, is initially 0 into the powder particle, that is why 0. At time t is equal to 0, basically not time is equal to TRP, TRP means after the residence time, TRP means when the particle will reach the top slag, that is called the residence time of the particle. So, at t is equal to TRP, basically the concentration into the impurity will be corresponds to the concentration, that is that concentration I am defining at, that is when the particle will join the slag phase, then it will have a concentration of CSLF, F means final, that is the top layer when it is joining. So, final. So, it will be the concentration into the powder finally when it will reach the top slag. So, CS stands for the slag, L stands for the liquid, and F stands for your final. So, when the powder particle will reach the top surface, then it will have this concentration. So, then I have taken this term on the denominator. So, we can, and I have taken the VL on this denominator on the right hand side, and then I can simply integrate it 0 to TRP, concentration this to this. Now, if I assume that is the CMB is constant, actually it is slightly will be constant, theoretically it will be changing, but during the rise of the particle, that is the powder particle, we can assume that is the change in concentration in the metal concentration is not significant. Okay. So, if I just ignore that, then it is then the variable only this thing, and then we can simply integrate this equation, and then finally if you get that, you can simply after integrate, you can integrate and get this relationship. So, when the powder, the liquid powder will reach the top slag, then its concentration will be given by this, where L is the partition coefficient, CMB is the instantaneous concentration into the bulk, okay, bulk metal phase, and 1 minus AP is the contact area of the FRP and the liquid metal, and Kp is the mass transfer coefficient at the FRP liquid metal concentration layer and boundary layer, and L is the partition coefficient. VPL, as I said, VPL is the volume of the free rising liquid particle, and TRP is the residence time of the particle. So, then you can simply get this relationship, that is the when the powder will be loaded with the impurity, and when will reach the surface, then its concentration will be given by this, simply by this. And similarly the final concentration in the FRB, that is the free rising bubble, and the particle attached to the free rising bubble, and that concentration also similarly can be given by this, that is the when the particles being attached to the bubble is moving and joining the top slag, then the concentration of impurity for the particles attached to the bubble will be given by this. And simply the similar equation, only Ag represent, that is the total interfacial, there is a interfacial area in the at the particle liquid interface when the particles are attached to the bubbles, for those particles which are attached to the bubble, and Kg is the mass transfer coefficient again at the interface, particle liquid interface, for those particles which are attached to the bubble, and then Vpg is basically the volume of the particles attached to the bubbles. TRV is basically the residence time of those particles inside the liquid, residence time, okay, because that is the residence time of the bubble, because the particles are attached to the bubble and it is moving with the bubble with the same terminal velocity that of the bubble, okay. So, then this is the expression you can get. Once we have calculated, that is what will be the impurity concentration in the powder particle, there is the liquid free FRP, there is the free rising particle, when they reach the top slag, we have calculated what will be the concentration of the impurity into the powder particle just now. We have also calculated if a particle attached to the bubble, when it will reach the top slag, then what will be the concentration of the impurity in the particle. So, once we have done that thing, now we can write the overall rate as we have expressed previously. So, the final rate equation may be written as this thing, that is the minus of dCMB dt, basically V I have taken on the right hand side. If I take this, because you can see it is CMB into this term, this plus this term, and all have a unit of per second. You can see AF Kf by V, this is called the rate constant per second, it has unit, because mass transfer coefficient at the permanent slag metal interface, and it has a unit of centimeter per second, and area has an area of centimeter square, and this is the volume. So basically it is centimeter cube per second, and it is centimeter cube. So this is a unit of per second. So it becomes a rate constant. It is the rate constant at the permanent contact zone. Okay. Similarly, this is the rate constant at the free rising particle, and this is the rate constant at the free rising bubble, that is the particle attached with the free rising bubble. Okay. So this is the rate constant there. So the three rate constants, so I can write this equation minus of dCmB dt is equal to Cmb into A plus B plus C, where basically, and then also it is a minus sign is there, basically here we have a minus sign is there, minus. Okay, so minus of dCmB dt is equal to Cmb A plus B plus C, where A, B, C are simply rate constant at the permanent contact zone, at the free rising particle, at the free rising bubble interface. Okay, so now the relative contribution of the free rising particle we can write simply like this: B by A plus B plus C, and then the relative contribution at the particle attached to the bubble, particle attached to the free rising bubble at C by A plus B plus C, and similarly we can say relative contribution of the permanent contact will be given by A plus B plus C. So now if we can calculate the rate parameters, the rate constant at the permanent contact, free rising particle and the bubble interface, and the free rising bubble FRB, or the particle attached with the bubble, that interface. So then I can get the relative contribution of the FRP, PAB, particle attached with the bubble, and the permanent contact given by this. So, so now how you can calculate some of the calculation I am showing you, that is the how to calculate the area and the volume parameters. So this is the total volume of the free rising particle. Total volume can be given by, suppose W is basically the injection rate, that is the amount of powder injected per unit time, and rho s is the density of the powder particle. So this is the volume injected per unit time, and out of which let us say F fraction that is attached with the bubbles. So attached with the bubble, so VPG, this is basically the volume of the PAB, particle attached with the bubble, VPG, that can be given by W by rho s into F. F is the fraction of the powder particle, volume fraction of the powder particle that get attached with the bubble. So VPG is W by rho s into F, where VPL, that is the total volume of the free rising particle, will be given by W by rho s into 1 minus F simply. And then AP is the contact area as the free rising particle, and if we assume there is the free rising particle are perfectly spherical, then we can write like this, that is the 6V, that is the volume of the particle by dP. So that will be the, assuming that is the free rising particle, if we assume sphere, then this is the effective, actually from the volume and the diameter of the particle, average diameter of the particle, we can calculate the total contact area of the free rising particle with the liquid. And similarly AG, that is the basically the surface area, that is the surface area interfacial area of the particle attached with the bubble, that can be calculated by number of bubbles, and that this is basically the area of the free rising spherical cap bubble. Okay, and the area means basically if you have a free rising bubble, see like this is the free rising bubble, and this area we are considering, this is the area, bottom area. So this area can be given by pi x square by 4, where x is the diameter of the base of the spherical cap bubble. Okay, so this is the area, and this is the M, basically the fraction of the area that is attached with the This is, suppose this much is a particle attached with the bubble, this is the particle attached with the bubble, this is the PAB, particle attached with the bubble is this much, that is the m fraction of that area, and total number of bubbles, then you can get the total interfacial of the PAB with the liquid, right? Okay, so that you can get. And then so x is the diameter of whatever say, and then you can Q bath also, basically the QSTP, that is the volumetric flow rate of the gas. We know, we need to know what is the actual flow rate or actual gas volume when they entered into the liquid still, that you can simply get by T bath by 298. You can make the temperature correction, and then number of bubbles you can get divided by the volume of the bubble, and then basically you can get, this is the total volume, this is the volume of a particular bubble, and so number of bubbles you can get multiplied by the TRB. So this is basically the volumetric flow rate of the gas, okay, volume per unit time multiplied by the residence time, that it gives you the total volume of the bubble, okay, divided by the volume of a particular bubble, that gives you number of bubbles, and then you can calculate the Ag through it. So based on this, we can calculate the different parameters for rate constant A, B and C, and when you know the A, B, C, we can simply calculate what is the relative contribution of different parameters. So then we can calculate the relative rate of different contact zone, okay. So we can calculate the relative contribution of different contacts this way, and some problem will be given from there, interesting problem will be there. So you can now calculate a different contact how much contribution will be there. So in conclusion, we can say there is a submerged injection of calcium powder is essential for the calcium powder. There is a submerged injection is essential for the calcium powder, which is basically very reactive and volatile. And two major techniques are that exist are, after one is that injection by the submerged lens, and second is injection by cold wear injection. Cold wear injection, where basically a cold wear injection. Two major techniques: injection by submerged lens and the cold wear injection. Okay. And during the powder injection by submerged lens, three parallel reactions take place simultaneously, as we said. One is the permanent contact slag metal interface, and two in the transitory contact. One is the free rising particle and the free rising bubble interface. And all these three reactions take place parallelly. So effectively, the total rate of the reaction is a combination of these three rates. And the relative contribution at all three contact can be established, as we have seen, that is all the parameter can be calculated. And basically at high starting speed, when the top slag, basically you will see there is a permanent contact is usually less than the transitory contact when the starting is very mild. When the starting is very strong, basically when the liquid slag emulsifies significantly into the liquid metal, then the interfacial area at the slag metal interface also increases, permanent contact increases significantly. Then the permanent contact, there is a rate at the permanent contact becomes high, and that can exceed the transitory contact reactions. Usually the transitory contact reaction is very high because of interfacial area. At the transitory contact, small droplets and bubbles are moving, so lot of surface area is there. So even at the low mild starting when you are doing, then the transitory contact contribution become more than that of the permanent contact contribution. But when the starting rate is very high, when the top slag get emulsified into the metal, then the total interfacial area at the top slag metal interface also increases significantly, and the permanent contact contribution exceeds far beyond the transitory contact contribution. Okay. Thank you very much.